going to review a way now that is convenient for setting up a simulation in MATLAB. So what you do is you have one function file, we'll call it the system function file, and you can name it usually a name that refers to the system that you're studying. And in this file, I'll show you some examples. You can have some what I'll call intermediate system variable computations. It also defines and computes, most importantly, the system state derivatives. These are the terms that populate, if you like, the state equations, because you have to send those as an output, and I'll show you some examples shortly. And this file can also have a set of output equations, and I'll explain why it can be convenient to do this, especially when you're trying to first of all do some very practical things with your simulations, but it's also very helpful when you're trying to debug your simulation to see certain variables that can be useful in helping you interpret what's going on with your model. So that is the first case, and again, we'll talk about how these are built for different kinds of problem examples, and then call it a simulation file. And this one, I'd like to name it, usually the name of the system file here is one convenient way, and then call it your sim file. This is an M file in MATLAB, a script file. It sets up all the parameters. So here's a way where you can organize and manage all the data for your system. There can be tables, there can be especially making sure that all the parameters have units consistency. Here's where you can do all those calculations. Sometimes you set up options for your ODE solvers, and then it handles and manages all the running of the simulations. Maybe there could be multiple ones that you're running, multiple cases, and then of course those make calls to the ODE solvers, and then finally it does any post-processing of the results, either displaying on graphs, saving to files, whatever the case might be. So here's a simple illustration of, really I call this the sim file, but really I'm talking about the system function file here. The sim file is really referring to the file here that is sort of handling, bringing in initial conditions, calling the ODE solver, and handling communications with the function file. So here's an example with the equations from the simple pendulum. And keep in mind that every call to a solver is making multiple and actually what I should be showing here is that this sim file really calls an ODE solver. So this is kind of incorrect the way it is. You can think of the ODE solver is embedded here, and that's really what's making multiple calls to this function file. And then the sim file, might call the ODE solver. That subroutine then makes multiple calls to your function file. And I'm showing two different ways that you can build this function file. Each of these files should start off, and this is a requirement of MATLAB, you declare it as a function as the first line, and this term x dot here, and you can call this anything, but it's the derivative of x, if you like, and I commonly will use this, but you can use any variable here that you want. This is going to contain the vector of state derivatives, and it returns those to your calling routine, which in this case would be an ODE solver, but you could actually call this from a simple command line. And what you do here is you define, and this name here that you would use, and I'm using pendulum equations, the name of the file would then be pendulumequations.m, right? So you'll see that when you create this first line and whatever name you put here, it's then going to say, pendulum equations. It's going to prompt you to save it with this name. Okay. The next line that's useful to put in here is a global statement, and here you would list any variables that you're going to need for calculation inside this subroutine. This global statement should have a matching global statement in in your simulation file. So you would have like global G and L here. This declares these variables so that they can be seen, in this function file, which is expressed here, right? Because you need to have these variables known. These variables will not automatically be seen by function files. They'll be seen within the workspace. This contains the workspace in MATLAB that you're working in. But when you define variables inside this subroutine, the workspace variables are not going to be seen unless you declare them global. And if you're familiar with other programming languages where you make global or common statements, it's the same thing. The next thing that you want to do is remember this X here is a vector, the vector of states, vector of state variable values. And so it's just a vector of numbers, and it'll be size n. So in this case, the pendulum equation had n equals 2. So what I like to do in here, you can do this a lot of different ways, but I like to name a new variable using physical, a variable that I can then look at and easily debug. And then I didn't follow through. What I would normally do is then in here, instead of saying sine of x1, which you might forget, if you get a very complex program, you forget what x of 1 is. In here, I would put theta. And you see then this line here, and you could even call this, theta dot 2, right? And that would be your theta dot equation. That way it looks like this equation here. You see it's minus g times sine, and x1 here is theta. And see what I'm saying is when you're debugging, it makes it easy to make sure that you haven't made any mistakes here. And like instead of using x2 here, I would use theta dot, right? Because this is basically saying that x dot 1 is equal to theta dot, which that's what you're declaring there, right? So I would use the variable name instead. And then what you do is you create for output this vector here of those derivatives, right? So this is what you're creating. You're creating basically this x dot value now evaluated at the value of those states. I hope that you have seen the use of function files like this, and this is simply just reinforcing that. If not, it will be helpful to you as you go forward and work some examples. Okay. Now, I've shown another way to do it here, and I'm going to take some time to explain this because I have found this very useful. Before, what we would do is really struggle with the fact that if I made any computations in this function, they cannot be seen, in the normal workspace, as I just mentioned. So one of the things that you can do is you can define, so notice how here the only output that's coming out here is x dot. Well, you can also ask this same function that you're using to compute state derivatives, and by the way, MATLAB will prompt you nowadays to put a comma here instead of a space, because this is a 2x1 vector, so put a comma there, or it's a row. So this allows you to send out values in this y vector as well. So everything is the same here, except note that I've added below the derivatives down here, I can start adding y definitions. And here I'm saying, hey, I computed x dot 2 here. And by the way, that's basically x dot 2 is the acceleration, the angular acceleration. It's being computed every time step. I would like at some point to also be able to ask what is that value, and I'm going to show you how this can be used. So what I'm saying is and I'm going to show multiple examples where we'll compute certain intermediate values here that would not come out of this function through the state or vector here, but you can request those in this y vector, and it's very useful. It might be best to see an example, and I'll show you shortly. So really this just summarizes that the simulation file, you set that up to make calls to solvers such as RX4 fixed, right? So here's an example where you would you would create this file. It's just a script file in MATLAB. You create, here's your global declaration. Here's your definition of and note, as I sometimes like to put a comment here, and I'll put an A. That's my gravitational acceleration. I didn't do it here. And also, by the way, the units are in meters squared per second. I'll like to put units in here as well. And then I'm computing a value for L here. You could either give it a value, or you could give it a value based on some calculations. Here I actually calculated L so I could make the certain period of oscillation for small amplitude is equal to 1. Don't worry so much about that. But G and L are defined globally, and now I can use them in my calculations. Next step in a simulation is you want to set up initial conditions. Now, we'll talk more about initial conditions in other examples, but you need to tell it what are the initial conditions for, in this case, theta and theta dot. And for a pendulum, it's pretty easy. You can say, I'm going to release the pendulum from rest at a certain angle. Well, that's going to define your initial angle. It's going to define from rest means, a theta dot of 0 equals 0. So there's going to be some cases like this where it's easy to set those initial conditions up. In other cases, as we mentioned before, you need to be very careful how you define this initial condition vector. Then you need to place it in your definition of an initial condition vector because it's going to be needed by your simulation call. Then you need to give it time information. What's my initial time? What's my final time? What's my time step in case of a fixed step solver? How many steps based on delta time? You'll have to go back and study these little calculations. There's not a whole lot of detail here, but it might be worth going through it as you work your own examples, as I ask you to work these as parts of homework or as parts of exercises. Finally, here's your call to, in this case, RK4 fixed. I've put in the time, initial time, final time in this time span. Here's my initial condition vector, number of steps. You call pendulum equations, then all the time values, all the x values, the two states over all those time values comes back, right? T is a vector of size, whatever n is, right? And then for a fixed step, you know what that is. And x is going to be, not only is it size n, but and then also it has, right, for each state, it's going to have n values. So it's going to be a matrix of whatever little n is, which is the number of states by n. So it's an array, right? For every time value, you have two states in this case. And then you set up whatever plotting that you want. Okay. I'll expect that you have put yourself through a MATLAB example review on things like plotting, or are familiar with it from, as I said, past classes and usage. And this just shows the results of a simple pendulum released from rest. And I calculated in that plot the total energy. For RK4 fixed, it stays pretty constant. You recall when we worked this as a simple example before using an Euler, the energy does tend to climb when you have too large a time step, showing that you've got some error in your numerical integration. I already made some comments on initial conditions, but I really want to emphasize, don't overlook properly defining those and taking the time to make sure that you're defining your initial conditions properly for your, not only for the problem statement that you have, but also that is consistent with your system. Again, for simple systems, they're pretty easy. Like I showed for the pendulum, they're pretty obvious. For each state in the system, you're going to have a corresponding initial condition, and this contributes to the initial condition vector that will be required by the solver. It's important to remember again that these initial conditions, when you look at the whole, system state definition, the initial conditions means that you're defining this and it has to be consistent for the whole system of equations. So you cannot arbitrarily set initial conditions. You can't just set them any way you want. They're related through these system of equations. So this is how you find initial conditions. Is sometimes we'll say we're going to start it from an equilibrium. We'll set this equal to 0, right? And then from there we'll solve what should be the initial conditions now for x naught, and I might set the inputs to be at a certain value, and then for those given values, for my derivative equal to 0, I'll solve for this initial condition vector, and that'll give me an initial state at an equilibrium that I can use for starting off my simulation. Okay, that might be a lot for some of you to take in right away. You'll see it demonstrated, as I said, in some examples. Lastly, in this little short discussion, what to do when there's something wrong. This could be a very long discussion, but there's always something that's going to go wrong. You should expect it. Later, we might discuss problems that can be corrected from the model itself. There's things like, checking the sign on terms. You have to be careful when you're also just simple typos can sometimes wreak havoc. There's error messages that will be generated. They help you narrow down the problems. That's why it's nice to run RK for fixed or a fixed step solver, because you can find out if there's some fundamental problems in your code before you start investigating whether there's something wrong with the actual system. So code debugging, you should expect that that's going to be part of what we do here. Learning how to debug is a key part of learning how to build these kinds of models. I think debugging also forces you to review and kind of reinforce understanding of syntax, right? And it also helps you refine and make the code more efficient. As you're going through looking for errors, you're cleaning it up, trying to make it a little bit more efficient. I have found that that's a very good practice for myself. And as I said, using a fixed step solver at first helps you get some information back that helps you debug. Next, we'll look at some simple examples.